Good afternoon, everybody. Welcome to the very first webcast of Public Community Webcasts brought to you by Microsoft Global Business Support, Middle East and Africa. My name is Mehmet Aras. I'm a premier field engineer working at Microsoft. I provide development support to our customers out on the field with their development-related needs and objectives. In our webcast today, we are going to talk about software principles and code quality. But before we get started, I would like to point out some of the other webcasts we have coming up so that you're aware of these fine webcasts coming your way so you can attend and learn about our products and use them effectively. You can go visit our website. You can see the address URL up here. And then you can see the other upcoming webcasts in April, May, and June. Now, today we are going to talk about code quality and software principles. And before I start with my main presentation, in order to give you a real-world scenario and the context that kind of inspired this webcast, I'd like to show you some numbers and some incidents to kind of give you a real-world incidents out there. Now, this data, I'm going to put these numbers out here, is a couple of years old. They kind of highlight some of the issues in software or in general IT industry. So software bugs cost the U.S. economy an estimated $60 billion every year. On average, professional coder makes about 100 to 150 errors in every 1,000 lines of code that they write. And last year, canceled project costs firms almost $67 billion. An overrun or maybe mismanaged project racked up another $21 billion. And these are big numbers. And some concrete examples that we can see what happens when things go bad. Some unfortunate incidents, perhaps. This is a ship from U.S. Navy, and what happened is that a crewman entered 0 in a data entry field of an application that controls the propulsion system, and that caused a divide by 0 error and shut down the entire propulsion system of the ship. And the ship was dead in water, just stopped in the water for 2 hours and 45 minutes. Completely vulnerable, and luckily in this time they were not in a war kind of situation, so they were just a sitting duck, but nothing major happened. But you can imagine the other ways that this could have turned out. And there's another incident. This is a Ariane 5 Flight 501, so launching some satellites out in the orbit. And what they did is that they decided to reuse the same code base as the previous flight, Ariane 4, which there's nothing wrong with that. But what happened is that there were a couple of issues. For example, this flight had a different flight path than the previous one. And then, so they had to do some, the conversions from, for example, 64-bit floating point to 16-bit signed integer. And the software engineer also decided to remove the exception handler for performance reasons. And as a result, this Ariane 5 Flight 501 actually exploded up in the air because of an exception occurred. And the cost was $370 million at 1996 prices. So these are really big numbers. And if you look at it, the code that led to that kind of a result is actually very minuscule, very simple. And there's another example, F-22 Raptor. This was deployed to a mission overseas Japan for the first time. And when this beautiful airplane crossed the international date line, somewhere in the middle of the ocean, the computer crashed, losing all navigation and communication systems. And luckily in this case, it was clear weather, so the pilot was able to fly back to Hawaii, just following the tankers, just flying low and just following some ships and tankers. And imagine this wasn't the case. This airplane could have crashed and hopefully not killing the pilot, but it could have turned out very badly. Some may be more interesting cases. These are some of the error messages that we see from applications that we use daily, day in and day out. For example, this is from Visual Studio Setup. Apparently, Microsoft is not immune to these kinds of things. So this is telling us that we need to shut down Windows.system. So good luck trying that. Another one, we are copying some files, and it's about 2.31 gigabytes. And up there, it's just telling us that we have about 10,000 days and 20 hours remaining. But it's going to be a long time until that copying is over. And here's another funny one that tells us that an error has occurred while displaying the error that has occurred while creating an error report. That's just a funny one. I'm sure you have your favorite one. This is another one from an old version of Microsoft SQL Server Management Studio. It's apparently run into some sort of an issue. It's giving us a warning, but there's really nothing here for us to even search, find out what the issue is. So the question here is that how can we prevent these situations? How can we make some of these issues from silly cases to catastrophic cases? So my webcast today is going to be all about that. So let's switch back to my presentation. So, as I said, my name is Mehmet Aras, and I provide development support to Microsoft customers. Prior to joining to Microsoft, I had a lot of experience developing software, from real-time systems to financial applications. And I've seen so many code that have become less maintainable over the time. And as a result, the quality suffered. The number of the chances of introducing bugs increased tremendously. So in this talk, I'm going to talk about some of the principles that we can apply to keep our code better, our design simple and more maintainable. And also I'm going to talk about code quality and some of the tools and processes that help us keep that code clean and pristine. So first, let's define quality. Quality, you can find a lot of definitions, but here, degree to which a set of inherent characteristics fulfills requirements, or another one, the characteristics of a product or a service that bear on its ability to satisfy stated or implied needs, a product or a service of deficiencies. So basically, a product, in our case, a software application, needs to provide the services that we expect, our requirements. That software application needs to fulfill those requirements in a manner that we expect, we as users expect from that application. There are also implicit expectations. For example, I expect that application to perform well, or maybe security, right? Maybe a good user interface, that I don't have to spend a lot of time to figure things out. Those are the some of the implied characteristics or requirements that I sort of expect from this application, but they really add up to the quality of the application. Now, quality needs to be present throughout the software development lifecycle, from gathering your requirements all the way to delivering your application and actually monitoring that application in the production. However, in this webcast, we are going to concentrate on development. How do we maintain quality in development? So this is going to be our focus area. So if you look at software development lifecycle, everything starts as a new project. And this is what we call greenfield. And greenfield is just basically a field that has a lot of green, like the grass on it, the trees. There has been no development done on it. So it's a brand new project. So this is your chance to actually start new, start with a clean slate. You can write a new code, new architecture, new technologies that you've been wanting to use. And you want to practice a lot of the things. And you know some of the issues in the past, so you don't want to repeat those issues, repeat those mistakes. And the team has a positive attitude at this point because it's a new project, everyone is excited, everyone wants to get on it and work and contribute. But what happens is that software applications are not like a paper tissue that you use it once and throw it away. Software applications have a very long cycle So you have multiple releases. So what happens is that you are going to release and go back and work on the next release on a new set of requirements, perhaps bugs, perhaps improvements. So in the next version that you are working on an application, that's no longer a greenfield application. It's now called a brownfield or a legacy application. Something is already there. You are just building into that application, making changes and making modifications. So at this point, you are still early on in the life cycle of this application. So the code is still clean. Architecture is fairly clean, nice, understandable. So not a lot of issues. So you get new changes, bug fixes, new features. Code base is growing and getting a bit complicated. You may see issues here and there that kind of tie you down in terms of the solutions that you want to implement, but it's still okay. You can still manage. It's not to a degree that kind of hindering you or making you less effective. But let's fast forward. So there have been multiple iterations, multiple releases of this application. Now again, we are dealing with a brownfield or a legacy application, but things are, this time is a bit different. All those little issues here and there, they kind of accumulated. They have grown into a big snowball effect. Now you are facing limitations due to the existing design and the code base. You can't really implement the things that you want to do because the code is resisting, right? So you come up with solutions that are less than ideal. So you do hacks. You hack the code because the code is not flexible that you can't really work with it. So you kind of adapt to the code rather than code adapting your solutions. And as a result, you can see like increase in the number of issues and bugs because code is highly complex, not understandable. It takes you longer to get things done. And also the chances of you introducing a bug increases tremendously. And another result of this is that your development release cycles take longer. If you don't understand something easily, if you can't make changes easily, if the software is resisting you, it's going to take longer to get those changes, get those ideas in. So your release cycles are going to take long, and it's going to increase the cost in terms of financial amount. And at this point, usually, the teams get together and discuss about a rewrite. I mean, the code has gotten so bad that the entire team is thinking about a rewrite. Rewriting the entire application that's been out there, God knows, for 2-3 years. The team is willing to rewrite it, and there are tremendous risks in doing that. And everyone thinks that the code is really, it stinks. No one wants to work with the code. And this is something that I've seen too often based on my previous experiences. I went through a rewrite. And this is something I see all too often when I go visit customers or in other projects that I'm aware of. So let's look at code smells. You remember I mentioned some of the issues with the code early on. Maybe they were small issues here and there, but over time those issues kind of accumulate and become a huge snowball. So let's look at some of the issues, what we call design or code smells. I mean, these are the smells that will capture your attention. They are not pleasant smells. So let's see what these are. Rigidity. I'm just going to put these out here so that you can see all the things that we see. Rigidity, fragility, immobility, and the other ones. Rigidity and fragility is just basically when you make a change in the code, it's so hard to get that change in because the code is so complex. You need to make changes in 100 other places to introduce one change in one place. You have that rigid and tightly coupled source code that it's not really allowing you to make any changes. Fragility, it kind of ties back into rigidity. Have you had a scenario where you make one change, compile your source code, and all of a sudden you get 100 errors? In some cases, the number of errors is so big that even the IDE that you are using is not able to display all of them, right? This is because the code is so fragile that you touch one area and it kind of cascades down into areas that you didn't even think about. Immobility. This is where I write code and I take it and use it elsewhere. Reusability is something that's kind of edged into our minds ever since the college, right? Write once, reuse it multiple times. Are you able to do this with your code? Are you able to easily grab a module, a DLL, and use it in another project and leverage your assets? Perhaps you are not, because when you bring that module from this project over to the other one, you are going to have to bring 100 other modules, because that module has tightly coupled with all the other things that you don't understand why, right? And it's easy to do the wrong thing than the right thing, right? This is oftentimes at Microsoft what we call is that falling into a pit of success. I mean, just like with everything else, falling into a pit happens naturally. Gravity does it for you. You don't actually climb a ladder, do anything to fall into a pit or a hole, right? You just find yourself at the bottom of it. So we say success should be like this, effortless. Now, you need to ask yourself, when you are doing things in the code, is your effort like that, just falling into a pit of success, falling into a pit of good design, clean code? Or the code is really fighting with you to get the design that you really are impressed and proud of yourself to come up with, right? Needless complexity. This is keep it simple, stupid principle. Do you see a lot of complexity in the code? Like maybe everyone is in love with patterns. Do you see unneeded use of patterns? You look at the code, it looks very complex for what it's supposed to do. A lot of patterns are used, but there's really no justification behind it. The code is sort of over-engineered for things that are yet to come, but they haven't. So we are designing for future rather than designing for simplicity, right? Needless repetition. We see this all too often, code repetition, copy and paste. You see something here, you are so afraid to make changes there, you simply copy that code, slap it into another place in your code base, right? This is very dangerous, because if the code that you just copied has bugs in it, issues, performance problems in it, you just duplicate it at some place. And if someone fixes it, are they going to remember to fix it in other places? Probably not. So really, if you fix a bug, if you do a performance improvement, and if someone has repeated themselves, then that bug and that performance is not going to be fixed, or is not going to be addressed elsewhere in your application. The last one is opacity. When you look at the code, are you able to understand without spending hours what the code is doing, what it intends to do? In some cases, you look at a piece of code, you spend hours, and you have no idea what the code is supposed to do. All the way from the naming conventions to lengthy procedures that over like hundreds and hundreds of lines of code that you just scroll a couple of lines down and then you forgot where you are, right? Is the code like this, or when you look at the code, the code is telling you exactly what you need to do without you resorting to some sort of a documentation or chasing down a colleague to actually explain you? Now, if you are seeing all these things in your code, or some of it, these are code smells, design smells, and they need to be addressed. And luckily, now before I get to that, the solution, there's really no silver bullet here. There's no a magic button or a magic configuration or a magic book that kind of has all the answers. The solution is multiple things, all coming together to keep your code maintainable, understandable, kind of get rid of those smells and the odors. Now, the first one is education and training. You need to be aware of the principles. You need to be aware of bad practices, anti-patterns, so that you can actually do something about it. Code metrics. You need to know, you need to gain some sort of an insight out of your code, right? Some sort of calculation, some sort of numbers that tell you whether your code is too complex, is it maintainable or not. So you can make some decisions. Static code analysis. Are you following best practices? Are you doing the things that you are supposed to do that's going to help you write that code that's going to perform, that's going to be easy to understand and maintain? Refactoring. This is another tool for software developers. Code, if you see optimizations, the improvements in the code, are you making those improvements? to ensure that your code going forward is always nice and clean. And when you see those opportunities, you take the time to actually to make the code changes to make it better. So that's refactoring. Now, there are other things such as knowing the software principles and using best practices. Mentoring, mentor and apprentice relationship. In your organization, you have high-level software developers that have a lot of experience and knowledge in their area. Are these people providing mentorship to newcomers? Do you have peer programming where you can actually transfer knowledge from one person to another one and give them an opportunity to interact? Code reviews. Is your team getting together periodically or at some point to kind of go take a look at a code and see issues? This would be a great learning experience for everyone on the team, and at the same time keep your code maintained and clean, and also a good social environment. So as you can see, there are a lot of things that you can do, not just one thing. And if you practice these things, if you bring these into your development environment, you should get clean, simple, elegant, quality code and design. And if you keep doing these things, your code is going to be maintainable. It's going to look like well-groomed garden. And this is the state that where we want to achieve and we want to remain, that desired state. Now, we talked about software principles in the previous slide I mentioned. There's a certain set of software principles. They are very core software principles that every software engineer should be aware of and should apply. And we are going to see these. And basically, it's just that if you put the first letters of these principles, it kind of spells out solid. A very well-known software professional in our industry called Uncle Bob Martin came up with this. Not the principles, but the top principles that you should know and the arrangement of them to kind of read solid. So it just basically says software development is not a Jenga game. Jenga is basically you throw all your blocks and you try to remove them without destroying the other ones. But if you look at this picture right here, your source code shouldn't look like this, all mess, all like a spaghetti code. It should be understandable. So in the next several slides, we are going to go over these principles. So let's take a look at these principles. I'm going to cover each and every one of them, but very quickly, the first one is single responsibility principle. Second, open-close principle. Lisco substitution principle. Interface segregation principle, and dependency immersion principle. Now, if you look at the first letters of these principles, it's gonna spell solid, and the goal is that have these know these principles, apply these principles to have a solid code. Solid in the sense that it's maintainable, it's understandable, it's loosely coupled. The code that actually works with you to actually come up with good solutions, good software designs. So the first one is single responsibility principle. It is very easy. The one responsibility and one reason to change. Separation of concerns and orthogonality. Basically, this means is that we see code that does a lot of stuff. You see a function, you see a class, you see a module that has a lot of responsibilities inside of it. It does a lot of things, and this is often called the perhaps a God object, an object that does everything. And the risk is there, if you are doing multiple things, and if I make a change in one responsibility, I may inadvertently introduce a bug in the other responsibilities, because I don't have that isolation. Everything is kind of all together, and they may affect each other. So let's see an example. So here I'm defining an interface called iDeveloper. Right, so this is object-oriented developer, object-oriented programming. I'm kind of coming up with an abstraction that describes what a developer does, and you can go and implement this thing in any way that you like. But if you look at this interface, we see that the developer can do design. The developer is supposed to code. The developer is supposed to refactor. The developer is supposed to do unit test, and the developer is supposed to do also load testing and release. Now, if you look at this thing, I mean, is this a good encapsulation of what a developer does? Are we adding more responsibilities than what a developer is supposed to do? I mean, at least in my opinion, we are. If you look at the last two on load testing and release management, this is sort of should be on a different role, maybe perhaps tester, performance tester, QA team. Now, the developer most definitely can work with that team, can help that team, but it's the main responsibilities of a developer should be design, code, refactor, and unit testing. Now, in most organizations, I mean, people wear multiple hats. So you can be a developer in the morning or a tester in the afternoon. That's perfectly fine. But assuming all these responsibilities from a developer is sort of like asking for trouble, right? Because release management, load testing have different set of activities and actions than code design, right? Coding and unit testing. Another example, we see this all too often, like when you do a design, UI design, you have all these UI controls and the events, and stuffing code into the event handler is a common problem. And all too often, those event handlers do way more than what they are supposed to do. In this example, we have a Vim form application, and on our main form, apparently we have a button, and on button click event, what we are doing is that apparently this is some sort of an application that allows you to buy stocks. So on the button click event handler, we are getting the selected stock symbol. Apparently the user has entered the stock that he or she is interested in on the UI. We are getting the selected stock symbol. And we have a stock symbol, stock transaction service that allows us to buy it. And then once that operation, that purchase operation is successful, we are changing the UI for either failed or success operation. But at the end of this button click event handler, we are also sending a notification to the client saying that, hey, this stock purchase was successful. Now, if you realize this is UI code, this is just some button click event handler behind UI. And I'm doing a lot of business code here, purchasing a stock, sending notifications. This should really belong in some sort of a business module, business class, not in the UI. UI code's main responsibility should be UI, the presentation. Right? The form code, the button event handler should concern with the UI elements, the button, the updating of the text box, not necessarily sending out notifications or knowing how to purchase stock price. So apparently in these two examples, we are violating single responsibility principle. So this is single responsibility principles, kind of nice picture. It says Swiss knife. We all know Swiss knife, that Swiss knife has a lot of tools, which comes in handy when you're in wilderness. But not in software development. Not in software development, we don't need a tool like this. If you have responsibilities, put them in separate places so that they can evolve and change independently of each other without affecting each other. So the next one is open-close principle. This basically states that new behavior should be added via extensions, not modifications. So let me show you what this means. Again, I have a class here, stock analysis, and it has a method, public method. It's called analyze stock. Apparently, I pass a stock symbol and a period that I want to analyze the performance of the stack over. So what the method does is that it gets the stock information, and apparently it gets the historical data on the stock, and then it calls a method called analyze. And the analysis, that analyze method actually implements some mathematical algorithm to kind of analyze the performance of the stack over that time period. Nothing wrong with this code, right? Looks normal. At this point, I don't see any problems with it. But let's say that your boss comes a couple of weeks down the road, or maybe a couple of months, says that, you know what, this stock analysis, the algorithm that we are using here, is good for financial sector or maybe the insurance sector. But however, we need a different algorithm for entertainment sector, perhaps. or some other sector. So what we want to do is that we want to change the algorithm. Now, your inclination should be to kind of open up this class, go into the analyze method, and make changes within this method. So kind of surgery, performing a surgery. But there are better ways of doing that. The better in the sense that as you make changes to this algorithm, the chances of you introducing a bug or kind of cause an undesired effect on the existing algorithm is actually high. You don't want to touch that. You want to leave that algorithm as it is. But you want to make your code flexible so that I can kind of plug in new algorithms without changing the existing algorithms. Now, this is what open-close principle says. New behavior should be added via extensions, not modifications. I don't want to modify this analyze method. I want to be able to extend it. Now, here's one way to do it, right? I can just come over here. I can simply make this analyze protected virtual. Now, if you are familiar with object-oriented programming, if I do protected virtual, if I do virtual, I'm just allowing the classes that derive from this stack analysis class to override this method. They can actually derive classes, can actually give their own implementation of analysis. And when I call an analyze stack method, it's going to call the derived classes implementation of analyze. So with a simple change, this protected virtual, and if you go back, this one was private. It wasn't virtual, right? I changed it to virtual. This way, derived classes, perhaps I'm going to derive a class called financial stack analysis that's going to change this algorithm. So I just made my class more extensible and follow the open-close principle. And another way, perhaps, there's another option that you can make it more flexible. So rather than you specifying the analysis algorithm inside, what you can do is that you can ask the caller to provide you that algorithm. Here, for example, I just have a property, getter and setter. It's looking for an analysis algorithm. It's asking the caller, look, I know kind of the workflow to analyze this thing. I need to get the stuck information, and then I call this the method to analyze it. I don't know what the method is, but if you want to do a stack analysis, this is sort of the workflow that you need to do. But the algorithm, I don't know. I'm just going to make a call to it, and you can just give it to me right here. And I'm going to give you a property where you can actually set that, and I'll just call it. As long as you actually give me a method that follows, that has this signature. Well, I mean, I just made this more flexible. So if you want different algorithms, that's fine. When you call the stack analysis classes analyze stack method, just before you do that, just specify, just set this property to the algorithm that you most appropriate for your stack, right? So this way, I'm just following the open-close principle. And here's a nice picture to kind of depict this principle, right? Over here on the right-hand side, we are doing kind of like an open heart surgery to get the changes in. Now, every time you do an open heart surgery, the risks are a lot, immense, right? But whereas over here, I'm not really doing any surgical thing. I'm just making things more extensible, and yet I'm achieving the same result. Now, which one would you go for? Of course, no one wants to get open heart surgery. Now, the next one is Liskov substitution principle. Now, this says that derived classes must be substitutable for their base classes without any problems or surprises. Now, let me explain this on an example. So here, I have a development team, and we are starting a new project. We are starting an iteration. We have a project, and I have my development team. I'm passing these to the start iteration method. So what we do is that for each team member, we get a requirement from our sprint backlog and assign it to a developer from our development team. So the developer is doing a design, code, and unit testing. It's pretty straightforward. Get a requirement, assign it to a developer, and the developer designs it, codes it, and unit tests it. So pretty straightforward. I wish, it was this straightforward in reality, but it's like a simple code that illustrates this. Let's see what happens in this next scenario. someone implements iDeveloper interface, and they provide an implementation for entry-level developer, right? Entry-level developer is a developer. But what they do is that, you know what, in our organization, entry-level developers, they cannot do design, right? So we are throwing a not implemented exception. So we are saying that, you know, this is an entry-level guy. We don't have enough confidence in this guy to do any design. So you want a more senior level person to take care of the design, right? Now, knowing this, let's look at the code above. What happens when I happen to grab an entry-level developer from the development team and assign that person a design? Your code is going to throw an exception. This is what Lisco substitution principle says. It says, okay, I'm working on an abstraction called iDeveloper. And anytime you pass me an object that implements iDeveloper, I should have the confidence to know that that interface, that abstraction is not going to surprise me. I'm not going to get any runtime issue, any runtime exception, because that's the interface I'm working on, or the abstract class, or the base class. And anything that you pass me at runtime that's derived from that, I should be able to call it without having any surprises. But in this case, I'm violating the substitution principle, right? As soon as I pass an entry-level developer to this method, their design, I'm going to get an exception at runtime, right? So basically what I'm doing is that I'm treating the different objects derived from iDeveloper differently. Now, let's see one naive way around this. And this is where we see one of a code smell. So let's see what the dev did here. This part is actually where the change is. So we get a design. We look at the developer. If the developer is an entry-level developer, is not an entry-level developer, sorry, we say that, okay, we are going to let this developer do the design. However, if the developer that we grab from the development team is an entry-level developer, we are going to go get a senior-level developer to do the design, right? So we are making a decision based on sort of the runtime type of this abstraction. Now, this is a smell, right? Now, this is violating the substitution principle, and instead of going back and fixing your abstraction, fixing your maybe the entry-level developer implementation, or maybe coming up with a better way to abstract this business rule, you are kind of working around this thing. Now, this is a smell. This is going to make the code less understandable. And imagine having things like this, hacks like this, throughout your code base over years and years and years of development. Now, that's going to make your code less maintainable. So let's go substitution principle. It just basically says, if something looks like a duck, quacks like a duck, but needs batteries, you probably have the wrong abstraction. In this case, I have an entry-level developer that I think is a developer, but apparently the entry-level developer cannot do design. But that kind of is not the abstraction or that I'm basing my implementation on. So the next one, interface segregation principle. So it just basically says that if you have a very crowded interface, this just basically also indicates that your interface kind of defines a lot of different responsibilities. It says, break it into multiple smaller interfaces. So let's see an example of this. So earlier, I had this iDeveloper interface that had a lot of responsibilities, right? Design code, refactor, unit test, load test, release. So in some, and I said that the developer, I mean, really developer shouldn't do load testing, release management, right? This is something that this is something that another team should take care of. Developer can help. But we know that in reality, developers do a lot of things. They wear a lot of different hats. I could be doing development in the morning, or I could be doing load testing or architecture stuff in the afternoon, right? But we can break this interface. I mean, we can account for the scenario and take that into account in our design. We can come over here, we can define multiple interfaces. I can break this I can break this iDeveloper interface into multiple different interfaces based on responsibilities. Look, up at the top, I have iDeveloper. And iDeveloper says a developer can do design, code, refactor, and unit testing. I also defined an interface called iTester. It says, hey, load test. You are going to do load testing, performance testing, that kind of stuff. And at the bottom, I have release management. And release management says, okay, release this application. Now, if I'm in an organization where developers do everything, that's fine. I just need to grab these interfaces and implement them. I can do iDeveloper, iTester, iRelease management implementation in one class. But if I'm in an organization where these responsibilities are fulfilled by different roles, then the developer is only going to implement this. And when I make changes to iTester or iRelease management, it's not going to affect the developers. Whereas in the previous case, if your release management procedure changes, guess what? It's going to affect the developers. And this is why single responsibility principle is so important. And kind of you see it working here too. So this is the photo kind of picture that's depicting this principle. Now, the next principle is dependency immersion principle. So it's just basically the dependency immersion principle states that don't take dependencies on concrete implementations. Take dependencies on abstractions in order to achieve loose coupling. Let's see what this is. Let's see this is in an example. So I have a stock transaction service, and it has a method, buy method. So I pass the client information, stock symbol, and the amount of stock that this client wants to purchase. Now, this buy method apparently needs to talk to a web service, needs to reach out to a web service to get stock symbol information. So I pass the stock symbol, and I get the stock information. And then I process that by purchase request. And then I get the stock transaction details, just the details about my transaction. And then apparently I have some sort of a data access layer where I store that information. Maybe this is a database or file, or I'm not so sure, but this is where I store those results. So what's wrong with this? I mean, initially when you look at this thing, you don't see any issues with this. It's pretty straightforward. However, if you think about unit testing this code, how are you going to unit test it? The unit testing should be something that the developer should be running all the time as I make changes. Now, each time I make a change, or each time I compile my code, I'm going to go reach out to a web service, get the results, and store it in a database. That's not very convenient. And plus, the web service or the database is not what I want to test. I want to test the logic in between those things, my code, not the external stuff, right? And also imagine the web service, you didn't write the web service. You are contacting someone else's web service, and they don't have a test web service for you. Or maybe you are paying each time you talk to this web service. How are you going to get this test, unit test going? You can't, because this code is making a lot of decisions, taking a lot of hard dependencies on these concrete implementations. Now, in order to fix this, I mean, the fix is very easy. I just need to immerse things, right? Now, that immersion, there are multiple ways that you can do this thing, but the most common one is that I rely on abstractions. Here, for example, I define two interfaces. One for the place where I will get my stock information. That's my contract. I don't care if I get the stock information from a web service, file system, anywhere. All I need is that information. Anyone who's providing that information, I'm fine. So I abstract it. And the second one is where I store my results, transaction results. I don't care where that data goes. I just define a contract, and whoever fulfills that contract, I'm perfectly fine with it. So I just abstracted away my two dependencies. And I'm not making any decisions as to who those dependencies are. I'm asking whoever is using me. In the constructor, I'm asking my caller, hey, look, I need these interfaces. Could you please provide me? You can do whatever. You can reach out to a web service. You can reach out to a file system. Anything that you like, any source, anything that implements these contracts, I'm perfectly fine. And you make that decision. I don't. I just make my class, this stack transaction service, more testable and more flexible. And if you look at the buy, right now I'm just using these interfaces. I no longer like new up these concrete types that only I can decide. I'm kind of inverting that decision and delegating that decision making to my callers. I'm not making any decisions. I'm simply relying on these abstractions, loosely coupling, right? So dependency injection. So this is our photo, kind of shows what it's about. You don't actually solder your cable into the plug, right? It's not flexible. Once you solder, you can't pull it out. You have that tight coupling. But if you have something like this up at the top, you can unplug, plug it into a different power outlet, and it's more flexible. Okay, moving on. I think we finished our solid, the principles that make up the solids, but there are a couple of others I think that are also important. This one is also very important, law of the meter. I often see this violated. So this just basically says that principle of least knowledge. Know just enough to get the things that you want to do. Nothing more, nothing less, right? So let's see this in action. So I have a post office class, and it has a method called mail. So it just says, give me the customer, the address that you are gonna sending this letter, and the letter, and I'm just gonna send it for you. Now, if you look at this implementation, the send methods reaches into the customer object to grab the address. So I just need to from address, right? I need to know from where to send this email to where. So in order to know the from address, I'm asking the customer. But I don't need anything else from this customer. All I need is the address. I'm unnecessarily tying myself to the customer object. And every time you make a change in the customer object, you are going to affect the post office and its mail method. Now, this dependency is unnecessary. If you look at the implementation, all the send method is doing is that reaching into this customer object to grab the address. So why have that dependency on customer object? I mean, here you can just ask what you need. All I need is an address from address. That's all I need. So why not ask that directly instead of asking something that contains from address? This is what the law of the meter does, principle of least knowledge. Know or ask just enough, not a bit more for what you need. Here I'm asking too much when I can do only with this piece of information. So this is your law of the meter. Now, so far I've talked about software principles. There are a ton of other ones. These are the most important ones. So so that's the principles side of our story. Now let's talk about tools and processes. There are a lot of principles to keep in mind, keep in track. What we need to do is we need tools and processes to help us. So code metrics, I mentioned this before. When I look at a piece of code, is there something that kind of summarizes me if the code is flexible or not, maintainable or not? Is there some sort of a calculation without me making my own decisions, kind of gives me indications? Static code analysis. Am I following the best practices? Am I doing something wrong from a performance-wise, from a security or the design points of view? So this is important. Code reviews. Are you getting together? Are you getting together with your team to take a look at a code and criticize it and find problems, find ways to optimize it, make it more clean? So that'll be the process side of things. Refactoring. Refactoring is an activity that the software developer should be doing on an ongoing basis. So once you write that code is not written in stone. 2 months down the road, you'll come back, maybe not even 2 months. Next day, you'll come back and you will see a better way of doing things. You will see, oh, I should change this thing because it's going to make it more simple, make it more readable. These are code refactorings. Without changing how the code behaves on the outside, you make changes internally to improve things, make things more simple, more cleaner, more flexible, more loosely coupled. Now, this is something that the software developer should be doing on an ongoing basis. This should be part of their daily activity. Mentoring. Not everything is about tools or some sort of a tool or a software that you download someplace. The humans, the human element of this process is also important. I look at my career and my past history. Most of the things that I learned through experience, my interactions with my peers, someone who's more experienced, taking the time to explain things, maybe places where I kind of screwed up, or maybe I failed, that person taking the time to show me how to do things, like maybe explaining software principles. I mean, this side is very important. Someone is actually showing you how to improve yourself, guiding you. The mentoring is very important because that becomes more personal and more memorable in your mind. Now, code metrics, I'm going to go over these little bit and details. Code metrics is a set of software measures that provide insight into your code and complexities within it. So basically, mathematicians and computer scientists with a lot of PhD degrees, with a lot of brains, they got together a long time ago, even now. They said, okay, how do we measure complexity? It is one thing to take a look at a code and make comments, but that's going to vary from person to person. We need something more objective. We need a set of calculations, a formula that I can point my code at. It kind of does some calculations and gives me a number. Now, that number is going to mean or indicate something, and it's not going to be subjective. I look at the code, I come up with things, you look at the code, you come up with your own things, and we argue day and night. But this number is going to be something mathematical, right? So this is what this is, code metrics. So if you look at this thing, there are a lot of calculations that give you different numbers, measure your code from different angles. One of them is cyclomatic complexity. This is all the conditional, different paths that you take within your code, all the conditional stuff. When you do if this, do this, if not, do that, that's a path. There are different execution paths that you are taking based on a condition. Now, as that decision making or the conditional execution paths increase, so does your cyclomatic complexity. Now, if this is big, right, that means you need to test each code that you can execute. So that means the cyclomatic complexity means that you need to have test cases for each of those conditional places where you can execute that code or not. That also means if the cyclomatic complexity is high, the code is going to become less understandable. Imagine you are looking at an if-else statement, like 30 or 40 of them, right? I've seen code like this, if-else, followed by hundreds of them. Now, if you want to add your own, how long do you think it's going to take you to find the right place to kind of find the right place to put the if-else? Next one is depth of inheritance. So if you have object-oriented programming, you have a lot of inheritance, which is good. But at the same time, if you make a change in the base class, that's going to affect the derived classes. So you want to take a look at your depth of inheritance. If it is too deep, it is something that you need to take a look and maybe see if there's anything you can do about it. Make sure that you haven't over-engineered anything. Hold on. Just hold on. I need to take a break.